we move on to vector error correction model. Johansson or cointegration tells that there is a long run relationship. But apart from that, you need to also know that it is not something like a railway track. There will be a movement here and there. It's not that the two tracks will move together. So if one of the variable is deviating from the equilibrium path, is it coming back again on the equilibrium path or not? This is given by vector error correction model. And this estimation is done after once we are sure that there is a cointegrating relationship between the variables. So for this you go to proc, and in proc, because this is, you cannot do it independently. It's not that I go to simply quick and I again somewhere I find vector error correction and then I do it. No, from the window where you have done Johansson cointegration, you will go to proc and select make vector autoregression. This new dialog box will open up, and if you have a look at it, it is similar to the one which was coming when we are selecting var. Now you will not select the standard var which you are doing it when we are doing selection of var. Rather, we will select on vector error correction. So once you select this VEC, this results come out. This is the term where it is the term designated as coint EQ1. This is the term which is of our importance. This is the error, this particular one, this point, that is minus 0.15. This is my ECT. This ECT means error correction term. Now, there were certain conditions, that is, it should be negative and it should be significant. But if you have a look over here, the T statistics, the figure in the parenthesis is T statistics. This is minus 1.29. And as a rule of thumb, if it is less than 2, then the variable is not significant. This is, although we will estimate it accurately, but as a rule of thumb, you can say that. Meaning thereby, although there is a presence of cointegration, there is no mechanism that if there is a deviation, the series will return back to its equilibrium path. So we cannot depend upon the estimates of this cointegrating relationship. Now we will have a look, and suppose, although here we do not have we do not have a significant error correction term, but suppose everything was fine, then in that case, now we want to estimate each and one variable over there, all the long run coefficients and the short run coefficients and all those things. Now you go to proc and then you go for option make system, and therein you have two options. You can order all the variables by you can order the terms by variable or by lag. We will select it by variable. This dialog box will be coming up. We are concerned with the first equation. Herein, this term from here to here, that is indicated by C1, is my error correction term up till here, and then you have C2, which is taking a lag of 1 for x, then C3 lag of x, lag of 2 for x, then C4 lag of 1 for y, C5 lag of y variable by 2, then C6 lag of z variable by 1, and lag of z variable for 2, indicated by C7. So C1 to C7 are our variables of interest. Then again you go to proc and then you select this estimate. Once you have selected this estimate, Another dialog box will be coming up, and we will do this estimation through ordinary least squares method. This is the result, and we were concerned with C6 or up to I think C7. C1 was your error correction term. Probability value is more than 0.05, that is, it is not significant. This is not significant. And if we have a look, not only this, but all the variables, the p values is more than 0.05, indicating none of them are significant. Once again, if you have co-integration, the other thing is what you can do is we can go for Granger causality test. So you again go to this option, you go for lag structure, the same how we have a calculated lag structure. Over here you select Granger causality or block exogeneity test. Once you select this, will be the output that is coming. Now this says that D does not Granger cause X because it is more than 0.05, not significant. Z also does not Granger cause X, as this one is also not significant. And if you similarly see whether X Granger causes Y, no. Z Granger causes Y, no. All of these are not significant. There is only one relationship which is significant, is Y Granger causes Z. So only this one is significant. Apart from that, all the relationships are not significant in terms of Granger causality. So this was the result of Granger causality. Now, once you have done this estimation of co-integration, whether your error correction term is valid also, so then you can go for your residual diagnostics test. So the moment you select this residual diagnostic test, all of these will be coming. A new dialog box would be coming up, and you will see there is an autocorrelation test, normality test, and heteroscedasticity test. All these tests you will be doing, and then you will be seeing that your error terms are normally distributed, the error terms have no serial correlation, and the error terms are homoscedastic. So after once you have checked all these things are fine, then only you can depend upon the estimates of your parameter. So in our case, the results were not good. So we take another data set quickly. The first thing which happens over here is the selection of the lag. Suppose they are all having unit root and you are differenced it. Now, once you have selected then you go in the var framework. So lag of 1 is again suggested over here. Then you perform Johansson co-integration test. Now this says there are two co-integrating equations. So you will get a different type of result from here. Then you can move on to, this is the process of normalization. It is there in the Johansson co-integration table only. This gives you are concerned. Your second concern is your error correction term. Your error correction term is negative. The value is 0.46. It is negative. It is less than 1. And if you see your t statistics, it is in the minus 2.41. So as a rule of thumb, this error correction term is significant, as we are having significant t statistics. So my error correction term is good over here. So then you can do the same C1 and C2. You can go for estimate equation, and we can see that C1, which was our error correction term, that is significant over here. Then you can go for your Bruch-Godfrey LM test, and we find that this Bruch-Godfrey test, this is the value, the second one, it is 0.84. So this means, what is the null hypothesis? There is no problem of serial correlation and my p-value is more than 0.05, so we accept the null hypothesis that there is no problem of serial correlation. Then you go for your probability test also. Here also you will find that the null hypothesis is accepted, and the null hypothesis is my error terms are normally distributed. As the p-value is more than 0.05, we accept the null hypothesis. So, and you can also do the remainder of the test likewise in the process. We were just showing you that there can be other results also, where there can be presence of two co-integration, the error current term is also significant, and then likewise you will check for the residuals and all those things. Next thing is we move on to the impulse response function. So from view only, in the VAR framework, basically you will get this impulse response function. Once you select on the impulse response function, an output with multiple graphs will be coming up. We are concerned with the response of x to y, response of z, x to z, response of again y to z, response of z to x, response of z to y. Let us interpret one of them. That is, what is the response of x to y? That there is initially there is a decline, and then the things relatively settles down and it goes towards again the original situation, but very slowly. Let us take some other case. Let us take this case of what is the response of y to z. So when there is a shock, first there is a decline, and then the things, there is a movement towards the positive side. So likewise you will be interpreting the results of impulse response function. Another thing that can be done there only in the framework of VAR, that is variance decomposition. You go to again in the VAR, you find the variance decomposition over here. Once upon you click, and these multiple tables will be coming. This is the variance decomposition of x, this one is for y, and this one is for z, and it gives you the terms. So it is only 0.07 and then 0.06 in the next period, and in period 4 it is 0.19. So likewise you get again for variance decomposition of y, for z in the first period it is 0, then the next period it is 0.28, then another in the period 3 it is 0.21. The next thing is the test of Toda Yamamoto. Now herein what you do, this is again done in the framework of VAR, and it is the process is just like the process of Granger causality. So you go for the selection of the lag structure, and therein you go for Granger causality in the VAR framework. This dialog box turns up, this output result turns up, and it shows which variable is Granger causing x, or what is y Granger causing x, is z Granger causing x, and we find that no, they are not Granger causing. Then what we do, we just incorporate an additional lag over here. In Toda Yamamoto, we just incorporate, in the same standard VAR, you just incorporate an additional lag over here. When we are doing VAR and all those things, it was only C. But in Toda Yamamoto, you write the variables, and then you put a sign of -1. You incorporate an additional lag. And your original variables are here, Z, X, and Y. So upon doing that, then this vector error correction output is coming, although it's of no use for us. Then on that, from that window, you will again go for lag structure, and again you will go for Granger causality test. Now you will get the result. This is the result of a modified version of Granger causality as suggested by Toda and Yamamoto. Now here, now see, if you recall our earlier discussion, in y was not Granger causing z, and x was also not Granger causing z. or these independent variables were not Granger causing the dependent variable. But here you can see this variable is 0.01. It is Granger causing, or it is causing, or there is a causal relationship between y and z. So this is how the Toda Yamamoto test is done. Only you need to just do a trick, and that is you increase one lag over there. So this will be the result, and you can interpret this result in terms of the causality in the Granger sense. Then lastly, we go to our method of ARDL, that is autoregressive distributed lag method. Now in this method, if you recall, it will be used when there is when the variables are of mixed order, meaning thereby one of them is, say, stationary at level and the other one is stationary at first difference. If this being the case, then uh, you will go to quick, and in quick you will go for, it's not visible over here, you will go for estimate equation, and in estimate equation, in here there will be an option of ARDL. So you will go to quick, you will estimate equation, and then you will select ARDL. So this out, once you have done, an output will come, but we are not very much concerned with the first output. Now once you have got the output of ARDL, then you go to view and you move on to coefficient diagnostics. In coefficient diagnostics, you move on to long run form of and bounds test. Now we get the value of bound test, and this is our thing of interest. F statistics, the value of it is 7.19, and we'll look at the 5% level, and this is the upper bound, and this one 3.1 is the lower bound. If my value of F statistics is less than the lower bound, no co-integration. If this value falls between 3.1 and 3.87, we are unsure, we cannot say there is co-integration or there is no co-integration. Only if my F statistics, which is 7.9, now in our case is more than the upper bound, which in our case is 3.87, then we can say that there is a co-integrating relationship between the variables. Next, we can again go for this view, and then there you will go for error correction model. When you go for the error, select the error correction model, you will get this output, and our concern is this co-integrating relationship equation. The coefficient of it is negative, it is less than 1, and the p, as the p value suggests, it is significant also. So from here we can say that by using the method of ARDL, we can say that there is a co-integrating relationship between the variables. But I repeat, it can be done only when there is a mixed level of stationarity, where some of the variables is stationary at level and some at first difference, and provided none of the variable become stationary only after second order differencing. So if it is the case that even after first order differencing the variable is not stationary, then we cannot use this method of ARDL. Then we go for residual diagnostics. We will, there the test, we will histogram, that is the normality, serial correlation, and heteroscedasticity. We do all of them. Apart from that, an important thing that is done is stability diagnostics. Now this stability diagnostics, it gives you from here you have to select two things you have to do over here. One is Kusum test and the other is Kusum squares test. Now this is the picture of Kusum test, and what we see that this blue line, it should lie between these two extreme lines. So if it is lying, then we can say that our model is stable. And this test was not there in Johansson co-integration, but when we go for ARDL method, we have to check whether our model is stable or not, and this is done through Kusum test, and the next one is Kusum squares test. So if suppose my blue line was somewhere crossing the point and again coming back, if this was the case, then we say that our model is not stable. ASYVARS, that is asymmetric vars. You simply write ASYVARS, and then over here in the next column you write which is the variable whose effect you want to see in a non-linear and this y, the variable which you want to decompose its impact by using a positive and a negative impact of it. So you have to indicate that we will be decomposing y into positive effect of y and negative impact of y. Then you go for make nonlinear ARDL. You have some. This is the result of nonlinear ARDL output. Now, if we see here, what happens when we take y positive, this is not significant. And when we take y negative, now this is significant. Means it is the same variable y, but when there is a positive change in y, it is not leading to any significant impact on the dependent variable. And when there is a negative change in y, it is leading to a significant impact on the dependent variable. So this is what we have over here, and this is what is an addition which we can do in the ARDL framework. And x variable is also significant. Here also we do all those other things which we are doing in ARDL. You will check for F statistics. This is the lower bound and the upper bound. My value of F statistics should be more than the upper bound value. So we can say that there is a co-integrating relationship between the variables. But here again we will check for our residual diagnostics. That is, we'll check for normality, for serial correlation, for heteroscedasticity. We will also do the stability diagnostics in terms of Kusum test and Kusum squares test. Apart from that, here from this window only of a nonlinear ARDL, we will also generate a non-linear multiplier graph, and this is the output of that graph. And this is one thing addition which needs to be done apart from the Kusum test and the Kusum square test, and this is done in the framework of an ARDL. So I hope today's lecture was clear to you. In today's lecture, basically this was an overview of all the many of the methods which we have covered in our discussions. We have first seen by using Eviews, we have seen how to do the graphs. Then we have moved on to the case of regression, that is estimation by ordinary least squares method. After that, we have moved to the next case wherein we have done the unit root tests. Once there is a presence of unit root and if it is the case where all the variables are stationary at first difference, then we go on to the Johansson co-integration test. Before that, we estimate the lag in the VAR framework, and then we go for the Johansson co-integration test. Once you are done with the Johansson co-integration, then we go for error correction model, vector error correction model. And if the error correction term is significant and less than 1 and negative, then we say that the model is fine provided the test of serial correlation, heteroscedasticity and normality are okay. Then we have also seen the case wherein you can do grandeur causality and you can do impulse response function and this variance decomposition in the framework of VAR. Then we have moved on to another case of causality, that is Todai and Yamamoto, and we have seen that it is done in the same framework of VAR, and we apply and interpret the output just like we have interpreted grandeur causality. Then finally, we have moved on to another method of co-integration, wherein we can do a co-integration even if there are mixed variables of mixed order. That is, some variable are stationary and some are stationary at first difference. And in this case, what we do, we estimate the bounds test. That is, we see the my f statistic should be more than the upper bound. Only then there is co-integration. And apart from the regular residual test, we also need to do the stability test in terms of Kusum and Kusum squares. Then we have done a modification of ARDL, that is the nonlinear ARDL. Herein you can decompose the impact on the independent variable into positive and negative impact and see how it is behaving with the dependent variable. And finally, again, apart from all the residual diagnostics and the stability test of Kusum and Kusum squares in NARDL, we also do a multiplier graph. Hope this lecture was clear to you. Thank you.